of my team winning is the number of games they win, 5, divided by the total number of games they play, 8.
It's kind of interesting, like with the distinction between odds and probability.
Note, odds are not probabilities. The odds are the ratio of something happening, i.e., my team winning, to something not happening, i.e., my team not winning. Probability is the ratio of something happening, i.e., my team winning, to everything that could happen, i.e., my team winning and losing.
So I think kind of visually that's like, so yeah, probability, I don't know. Yeah, I guess if you have like the sample space, I guess, and it's kind of like this, it's kind of like this, it's kind of like this. Yeah, it's kind of like this. It's kind of like this. Whatever, kind of like this. So maybe this is the outcome that your team wins, and this is when your team loses. So this is kind of like 50-50, but I kind of wanted to draw it like kind of like this, where it's like win and lose. And so if we said like the probability that your team wins is like 2/3, and the probability that your team loses is 1/3, I guess it's kind of like the odds are kind of like almost like throwing out this denominator and just being like, we're just comparing kind of like the ratio of these two events. And so we basically have kind of like 2-1 in this case. So the that is equal to so you can start off, it seems, with probabilities and get odds by just like dividing the probability of winning versus losing, because you're gonna get 2/3 over 1/3, and these denominator terms will will cancel out. You'll just be left with the odds 2-1. So you can kind of start with probabilities and get odds. Yeah, by kind of dividing in this way. It's just the relative kind of likelihood of two different events. It seems.
In the previous example, the odds in favor of my team winning the game are 5-3.
Yeah, and when you just see that, okay, we just talked about going from probability to odds. But can you go from odds to probability? So if we start off with the odds 5-3, what we're really talking about here is like this number 5/3, and I guess, I mean, just kind of just going the other way, like this is equal to the probability of my team winning over my team losing is equal to 5/3. I guess to kind of go in reverse, like you just kind of figure out what scaling term you need to apply to make these into probabilities. Like if you do, it's basically 5 over x plus 3 over x is equal to 1. And this is like 5 plus 3 over x is equal to 1. Multiply both sides by x. X. See, so now you've got 8 is equal to x. Kind of just feel like doing this. 5 over 3, x equals 1. We have 8 over x is equal to 1. And then, yeah, multiply both sides by x. So we have 8 is equal to x. So to kind of like retrieve these initial probabilities, like the probability of winning is equal to 5 over 8, and the probability of losing is equal to 3 over 8. And it's kind of weird. We're kind of assuming that these two events are mutually exclusive and collectively exhaustive. Yeah, it seemed like we could have. Yeah, we can just get this denominator term just by adding these two numbers. Like if our odds are like 5 to 3, then we just like add 5 plus 3, and like this is our denominator x. So the odds are 5 to 3, then the probability of winning is just equal to 5 over 5 plus 3, which is equal to 5 over 8. And the probability of losing is equal to 3 over 5 plus 3, which is equal to 3 over 8. Okay, so cool. Yeah, we went from odds to probability.
However,
I mean, it's also the case that I don't know. This is just like a weird like algebra point, honestly. But if you just have the probabilities like 5 over 8 and 3 over 8, you could say the probability of winning is 5 over 8, and like that's it. But I don't know. You can multiply like both these by 2 and like 10 over 16 and 6 over 16 like that. You can scale these up like however you want. So these are kind of the probabilities in lowest terms, least common terms, least terms. Forget what lowest terms. Irreducible fraction. Yeah, lowest terms, whatever. Uniqueness. Yeah.
probability of my team winning is the number of games they win, 5, divided by the total number of games they play, 8.
This is like a weird way to think about probability. I guess this is kind of like the frequentist view.
Here's the math. For the odds, we have the ratio of 5 to 3, and for the probability, we have the ratio of 5 to 8. Thus, we see that the odds in favor of my team winning are different from the probability of my team winning. Now that we know odds are different from probabilities, let's talk about how odds can be calculated from probabilities. In the last example, we saw that the odds of winning are 1.7. And the probability of winning is 0.625. We can also calculate the probability of losing. The probability of losing is 0.375. Note, we could also calculate the probability of losing as 1 minus the
Looking forward to when he gets to log odds. I'm curious about that.
probability of winning. That equals 1 minus 5 divided by 8. And that gives us 8 divided by 8 minus 5 divided by 8. And ultimately, we get 3 divided by 8. This is equal to 0.375. So either way, we get the same probability. Now let's take the ratio of the probability of winning to the probability of losing. Alternatively, we can put 1 minus the probability of winning into the denominator. Either way, we get the same ratio, 5 divided by 8 divided by 3 divided by 8. The 8's cancel out since they scale the numerator and the denominator by the exact same amount. Thus, the ratio of the probability ends up being the same thing as the ratio of the raw counts. And so either way, we get the same odds, 1.7. I mention this because about 50% of the time, you see odds calculated from counts. And the other 50% of the time, you will see odds calculated from probabilities. Either way, you get the same results. Note, out there in the wild world of statistics, you will often see this formula simplified to this.
Okay. Yeah, it's pretty interesting because I feel like I have seen that a bunch of times and it hasn't been intuitive, but kind of going through this example, it's, yeah, giving us the ratio between the likelihood of both of these events. Yes. Interesting.
Where P is the probability of winning. Bam! Now that we know what the odds are, let's talk about the log of the odds. Let's go back to the original example. In this example,
I just think real quick about the log. Like if you have two events which are equally likely, like the probability of winning is equal to 0.5, which is equal to the probability of losing, like you really have like a 50-50 split between winning and losing here. Then like yeah, then your odds are going to be probability of winning. Yeah, is equal to 0.5 or 0.5 is equal to 1. So if you take the log of 1, that says, I don't know, for example, log base 2, say 2 to what power is equal to 1, 2 to the 0 is equal to 1. So log of 1 is equal to 0. So basically, if the odds are even, if it's 50-50, then the log of those odds, I don't know, the log of like 50-50 is equal to 0. Oh, and then, yeah, so if you're less likely to win, like you say the log of, I don't know, 1 to 2, maybe, log base 2, 1 to 2, that's going to be equal to -1. And then I don't know if your log, if your team has a better chance of winning, it's kind of like 2 to 1. This is log base 2, then this is equal to 1. So it kind of shifts this thing. Like, yeah, it kind of shifts it. Before, odds were kind of like in the range of like, I guess odds went from like 0 up until like infinity, basically. Like, yeah, these were your odds. It's like a really good chance of your team winning, and your team has no chance of winning. Kind of shifts it from logs. So there's kind of like a 50-50 chance right here. This is like a 1, and then you just kind of go. It kind of shifts it to, does it shift it to basically infinity, negative infinity? I think it kind of shifts it to this, where like 1 would get shifted to 0, and then, yeah, I mean, this kind of tends towards like negative infinity, and then this kind of like just kind of like still tends towards infinity. Kind of shifts the range. I was kind of thinking of it being like computer science, where you go from like 1 indexing to 0 indexing. So kind of maybe the upshot here is like when you're in the 50-50 range, kind of when you're talking about odds. Okay, so you're 50-50, and you're talking about odds over here. 50-50 for odds is 1. Like the odds are 1 to 1. And then if you think about the log odds, then 50-50 is 0. And kind of like 1 to 2, if you're in the range, if you're kind of like 1 to 2 odds, then the odds are, yeah, I mean, 1/2, 1 to 2, whatever. But the log odds would be -1. And if your team is kind of like 2 to 1, then the odds would be, yeah, I mean, 2, +2, and the log odds, I guess, would be 1 in this case. So I guess like when your team has a better chance of winning, the log odds are kind of like scaled down. They only grow logarithmically. So they grow like much slower than the regular odds themselves. Because like if your team, let's just say friggin' you had like a 1,000 to 1 chance of winning, then the odds, this would be like a value of 1,000, but the log odds, let's just say that this is log base 10. This is just 3 in this case. The log odds are 3. So, I mean, if your log odds are 3, then your like chance that you win is crazy. I guess if we think like 999 to 1, this is kind of like a nicer way to compute the probability. Then you have like a 99.9% chance of winning. Yeah. Yeah. Cool.
We calculated the odds of winning as 1 to 4, or 0.25. If my team was worse, the odds of winning could be 1 to 8, or 0.125. And if my team was terrible, the odds of winning could be 1 to 16, or 0.063.
Looks like he's going to use log base 2.
And lastly, if my team was the worst, the odds of winning could be 1 to 32, or 0.031. We can see that the worse my team is, the odds of winning get closer and closer to 0. In other words, if the odds are against my team winning, then they will be between 0 and 1. Now, if my team was good, then the odds and 1. Odds are against my team winning, then they will be between 0 and 1.
Okay.
Now, if my team was good, then the odds might be 4-3 or 1.3 in favor of my team.
Yeah, I kind of want to just draw this out a little bit. So yeah, back in the kind of like odds universe, yeah, we kind of have 0 to 1, and then kind of 0 to 1, and then so here, this is when your team has a better chance of kind of losing, and then here, this is where your team has a better chance of winning. If your odds are in this range, then your team is favored. If your odds are in this range, then your team is losing. But if you do the log odds, then it's basically centered at 0 and kind of like this. It's like, honestly, we're talking about this like positive and negative infinity, but like in all practicality, we're really talking about here like these values are never going to be above like +5 or like -5, and that's even like being very generous. It's probably 3, positive, negative, 3, positive, negative. Well, it depends what base we're using. If we're using, log base 10, then like, you're never going to be. But anyway, so basically if we're in this range here, then our team has a better chance of losing. And if our team is over here, then we have a better chance of winning. Okay.
And if my team was better, the odds might be 8-3 or 2.
Just checking my phone real quick. Yeah, nothing.
7 in favor of winning. And if my team was really good, the odds might be 32-3 or 10.7 in favor of winning. We can see that the better my team is, the odds of winning start at 1 and just go up and up. In other words, if the odds are for my team winning, then they will be between 1 and infinity. Another way to look at this is with a number line. The odds of my team losing go from 0 to 1, and the odds of my team winning go from 1 to infinity and beyond. The asymmetry makes it difficult to compare the odds for or against my team winning. For example, if the odds are against 1 to 6, then the odds are 1 divided by 6, which equals 0.17. But if the odds are in favor, 6 to 1, then the odds are 6 divided by 1, which equals 6. The magnitude of these odds looks way smaller than these odds. Taking the log of the odds solves this problem by making everything symmetrical.
Oh, I didn't consider that part where comparing the odds. They're not using like the same units or something. Like these are kind of comparable cases here. Like you said, like the odds are kind of like 1 to 6 versus 6 to 1. Yeah, it's a good point. I mean, like these two are kind of like related in the same way, and you would want it to be the case that you would kind of want a measure of I don't know, like confidence that this team is winning and losing, and that kind of level of confidence you would want. Okay, he's talking about the magnitude. Yeah, the magnitude. You would want the magnitude of these two things to be. Yeah, you could want the magnitude of these two things to be the same thing. It's kind of like, this is kind of like it's kind of like this much in this direction and this much in this direction. It's kind of like the same. This is kind of like the line between winning and losing. Interesting.
Then these odds.
Let me just try it down real quick.
Taking the log of the odds solves this problem by making everything symmetrical. For example, if the odds are against 1 to 6, then the log of the odds, or the log of 1 divided by 6, which equals the log of 0.17, which equals negative 1.79. And if the odds are in favor, 6 to 1, then the log of the odds are the log of 6 divided by 1, which equals the log of 6, which equals 1.79. Using the log function, the distance from the origin, or 0, is the same for 1 to 6 or 6 to 1 odds. Double bam! Okay, now that we know the main idea about the log of the odds, let's get into some details. Earlier, we saw that odds can be calculated from counts. And we saw that the same odds could be calculated from probabilities. And that means we can calculate the log of the odds with counts or probabilities. Either way, we'll get the same value. Note, the log of the ratio of the probabilities is called the logit function, and it forms the basis for logistic regression.
Dang. Really? I didn't think logistic regression used log odds. Like, maybe I'm just thinking about it very differently, but it's like logistic regression, I thought you had some features and some parameters, and you just kind of calculated a score, and then you just piped it through the logistic function. The logistic function being, I thought it was just like 1 over e to the z, I guess, maybe like e to the z, something like this. I thought it was like this. I don't know where this kind of like log odds thing is coming from. I think I would need to do some more. All right, let me just ask ChatGPT real quick. One over 1 plus e to the negative z. Come on, ungray me. Oh, wait, where's the voice thing? I want to do the voice thing. I see that, but I'm watching a video which says that the logit function uses the log odds, like p over 1 minus p. And I'm not seeing the connection between that and the definition of the logistic function that you just provided.
Great question. The logit function and the sigmoid function are closely related, and understanding their connection helps clarify why logistic regression works the way it does. The logit function. The logit function is defined as text logit p equals logged frac p1 minus p right, where minus p is the probability of the positive class. This function takes a probability p, which is always between 0 and 1, and maps it to the entire real number line. Connecting logit to the sigmoid function. In logistic regression, we assume that the log odds logit function is a linear function of the input features. Log left frac p, 1 minus p, right equals wtx.
Logit function is defined as this. P is a probability of positive class. Function takes a probability P. Okay. Logistic regression, we assume the log odds is linear. Where is this? What? We assume that the log is a linear. Oh, you like make this assumption? The heck? The log odds solving for P. Get this, rearrange terms. That's exactly the sigmoid function. Logit function transforms probability. The logit function transforms a probability into log odds. Yeah. Take P and you just do P over 1 minus P and log. Okay. Sigmoid function is the inverse of the logit function. It takes log odds and converts them back into a probability. Oh. So yeah, let's think about that. So so we talked before about how to take odds and get probabilities out of them. Got odds to probability. But now I guess maybe we want to talk about like log odds, like take those and get them to probability. And you probably like intermediately want to convert them back to odds. So kind of think of this like so you have odds, maybe you have like 2 to 1, and then you do the log of that. The log is 2 of 2 to 1, and this is equal to 1. P over 1 minus P. So we kind of need this chain here where we start in terms of probabilities. So if I say 2 to 1, then it's basically like 2/3 over whatever, 2/3 to 1/3. Like these are our probabilities that we're starting with. And then we convert to odds. I guess pseudo converting to odds. Your odds could be, 2/3 to 1/3. Okay, we've based. I don't want to write this. Like our probability is 2/3 and 1/3. These are our kind of like probabilities. And then kind of going to odds, you have kind of like 2/3 to 1/3 odds. And then kind of going to like log odds, you do 2/3 over 1 minus 2/3. And then you take the log of that. So recall this is still just 2 to 1. So this is just going to be 1. You just kind of get an answer out of here. But now if you kind of want to go like inverse from this, you kind of start with like log of p over 1 minus p. And then, so how do we maybe get probabilities back? Well, this is log base 2, I guess, yeah, kind of like talking in terms of log base e here. So if we do e to this thing, then that'll just give us p over 1 minus p. And I guess we could do the thing before where we kind of like normalize these back into probabilities. Then, I mean, the probability of kind of winning is like p over p plus 1 minus p. And like the probability of losing is 1 minus p over p plus 1 minus p. I mean, just kind of like get those out. So yeah, that's how to kind of get back, but I think I was kind of missing the logit function or whatever. Let's see. The sigmoid function is the inverse of the logit function. It takes log odds and converts it back into probabilities. I don't know. Okay. Model always assumes that log odds are a linear function of the input. Dang. This is crazy. Sigmoid function converts these log odds back into a probability. Log odds perspective.
I mention it because if you do logistic regression, you'll see it a whole lot. It's no big deal. Okay, I get it. Odds are just the ratio of something happening to something not happening. And the log of the odds is just the log of the odds. What's the big deal? To show you what the big deal
What's the big deal?
all about, if I pick pairs of random numbers that add up to 100, for example, and use them to calculate the log of the odds and draw a histogram, the histogram is in the shape of a normal distribution. This makes the log of the odds useful for solving certain statistics problems, specifically ones where we are trying to determine probabilities about win or lose, or yes or no, or true or false type situations. Triple bam. In summary, the odds are just the ratio of something happening, i.e. my team winning, to something not happening, i.e. my team not winning.
Maybe just think about that. So it's kind of like if the odds are 2 to 1, so like what do we just kind of intuitively just immediately think from this? We think, oh, my team is twice as likely to win. Yeah, we do. We don't think in terms of like, all right, if they played 3 games, then I would win 3. Would win 2 times, and the other one would win 1 time. That's just weird. Twice as likely to win. This is just like a feel. It's like a feeling of yeah. I just think, and I mean, you could also say they have a 66% chance of winning. Yeah. I don't know. Odds, yeah, odds just like feel better, man. I don't know. 2 to 1, 3 to 1. Just like looking at these numbers. You wouldn't yeah, you wouldn't talk about log odds in terms of like intuition. You'd be like, yeah, the log odds of my team winning, bro, are negative 1.2. Like, fuck that. No. Log odds are just useful for statistics and stuff.
Log of the odds is just the log of the odds. It's no big deal. The log of the odds makes things symmetrical, easier to interpret,
Yeah.
and easier for fancy statistics. One last thing before we go. Even though the odds is a ratio, it's different from an odds ratio. But don't panic. We'll talk about the odds ratio in the next StatQuest. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you'd like to support StatQuest, well, like the video and consider buying 1 or 2 of my original songs. All right, until next time, quest on.
Thank you. Stats Quest with Josh Starmer. That was that was a great video. I enjoyed that. Revealing some of the connections between odds and loss. Really cool. Cool. Thank you. That was fun. See you guys later. Peace.